Everybody, we had a request to do section 8.5, the anti-Markovnikov addition of HBr to alkenes in the presence of peroxides. The peroxides change the whole mechanism. What is a peroxide? Well, as you know, they have an extra oxygen. That's where the name comes from, per extra oxide, oxygen. And when you have oxygen bonded to oxygen, that is a weak bond suffering from what? You guessed it, lone pair repulsions on adjacent atoms. And oxygen prefers being bonded to a less electronegative atom so that it can hog the electrons, as is its nature with its high electronegativity. So it's going to do whatever it takes to get rid of that OO bond. And how this reaction starts, it's unlike the more important reaction in this chapter with an initiation and 2 propagation steps when we substitute halogen for a hydrogen. That's the one we spent most of the time with in this chapter. We spent a little time with this one because it has some synthetic utility. And this one goes by way of 2 initiation steps. Call one initiation 1. And that breaks the weakest bond using the heat. So we have our dimethyl peroxide here. And the heat causes it to undergo homolysis. Homo meaning equally, and lysis cutting in 2 directions. So cutting it in half with both electrons being in the bond being split in half. And the heat's what caused that. So let's give the heat some credit. This is the only place you really need the heat to get this started. And what we have here, 2 methyl oxygen radicals. That's a radical. Has an unpaired electron. Now, that's a fairly polar radical. So it's looking to grab an H that's on the positive side. Unlike the other radicals in this chapter, I'm having issues being on the bottom of the screen here. Unlike in the other mechanism in section 8.1, where you grab an H off a carbon, which is a nonpolar bond, this is going to grab an H off of a polar bond, HBr being a candidate. And you're going to get what looks like a acid-base reaction, but because there's radicals involved, it's not an acid-base reaction at all. It's a hookup. 2 hooks meeting means you're going to make a bond between the O and the H. Where's the other half of the bond go? It generates a bromine radical. Bromine radical and methanol. Methanol. Methanol is done for the day. And the bromine radical is what's going to get the game started with the alkene in what we call propagation step 1. Propagation 1, bromine radical here is very unlike the bromine radical in section 8.1 and 8.2. This radical has the energy that better matches the energy of a pi bond. So it interacts with the pi bond and not with, like 8.1, an hydrogen atom attached to a carbon. This is a lower energy bromine radical. And, I don't think I like that 3rd hook. That explains, this 3rd hook explains what, something. It's going to go to you're going to put a radical on a secondary carbon when you had a choice of putting on a 3rd? I think not. Radicals are stabilized by the same things that stabilize cations. hyperconjugation is a big one. So where do you want a radical given a choice between tertiary and secondary? You want it on the tertiary. Your mechanism must reflect that. It says the other half goes to the tertiary carbon. So you've made a sigma bond between Br and the second C of the alkene, because by putting it there, you left behind a better a better radical right there. That's tertiary. That's a great radical. And in prop 2, that radical is going to grab an H. Where's it going to grab an H from? If I told you it grabs it from HBr, I hope you don't have a problem with that. Some of you might be saying right now, you reacted HBr. You can't use it again. What does initiation mean again? As you read chapter 8, you'll see initiation steps consume very small amounts. They're only to get this process started. So you've only, in theory, reacted 1 molecule of HBr. Now, if you're considering 1 molecule out of a mole of molecules, you still have a mole of HBr. So there is lots of HBr around. The propagation steps are what consume our reactants in this mechanism and the one in section 8.1, 8.2. And that's where you get the H. And that's an AntiMarkovnikov addition. And you have Br on the less substituted carbon and the H on the more substituted carbon. And it went this way because carbocations weren't involved, radicals were involved. And prop 1, you have to generate a carbon radical on the more stable carbon. So that's all you need to know about section 8.5. You won't be doing any delta H calculations for this section. You're only responsible for being able to predict the products. So pretend this was a blank on the test. Could you fill in the blank with this molecule? Or more likely, in part 4, you'll be given the reaction. You may be given the other product as well and asked to circle the major product, in which case it would look like this up here. And please don't circle this product. This would be the product if the peroxide wasn't present. And this is the product right here. And there you have it. And I just need to save this document so I don't lose it. Take 1 second. I should save it in the right spot, huh? There. Okay. Do you have any further questions about 8.5 before we think about our next segment?
Just I guess a few small thoughts. Okay.
Okay. Sorry about that. Here we go. Trying to
The
make it smaller.
so the reason okay, remind me again. You circled this one as the product. Is it because of the anti-Markovnikov or
Well,
is
it's
it
because this mechanism needs to generate in prop 1. This is the key here.
Oh,
You need
right.
to generate a carbon radical. And if you would put this hook on the other carbon, I'm going to put it here. I don't want you to put it on the test. Not Br here, because that would have put the radical there, and that's just not as stable. Secondary radicals have less hyperconjugation than a tertiary radical.
Okay, yeah. I see it now.
So it all comes only from that step. So yeah, good question, by the way.
And then the other like thought I'm having when I look at these, I don't know if it's specifically with the radicals, it almost like in my brain feels like resonance. Is that a wrong way to think about it?
Um, Are you
Just the
talking
way it kind
about
of
the general mechanisms themselves look like resonance?
in the way that I guess like where the because like where the radicals going and like everything else. I guess I don't know if it's just improper for me to think of it that way or if that might steer me in the wrong direction when I look at
Well,
mechanisms.
if you do think about this, moving electrons in a molecule to another position, that is resonance. So no, in your head, yes,
Okay.
there's some mechanism going on. Mechanism. There's always mechanism going on. There's some resonance-like activity here. Yes, but we're also gaining a bond to an atom, so that's a reaction.
Right.
So
I
think of
guess
it
the
like this part's like a resonance part, and this is a reaction part, and you generate this bond here and leave behind this nice radical.
yeah, I guess the ones that make me think about resonance the most are the ones where like the bond jumps over the O and like does all this and I'm like I guess to me I'm thinking it's like kind of going through the O and I don't know. It's just the way my brain is trying to like
Hmm.
visualize like what's happening because
Hmm.
it's just but I'm getting better at it. Anyway, moving on, I guess you mentioned the um the calculating with the thermodynamics and now that you
Yes.
mentioned that I don't know if we have an example that we could do with that, but also
Oh,
you
definitely we'll do one of those. Yeah.
okay, and also definitely following with 8.6 too.
Okay. So we'll do an 8.1/2 mechanism. Why don't we have the one of the allylic ones because you mentioned those earlier,
Yeah.
and then we'll come up with the other topic after that segment.
Okie doke.
So I'll have something for you when we come back, and we'll take it from there.
Okay, thanks.
You're welcome.